Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. Well, in this hour, we're going to throw the lines open because this hour is your hour. Let's get right to the first listener phone call.
Hello, Dr. Kaku. This is Wayne from Michigan. Exactly how did Einstein arrive at the speed of light squared in his famous equation? I know he's famous for his thought experiments, but did he use complicated mathematical proofs and equations, or what?
Okay, well, let me go through the thought processes that he went through. As I mentioned, when he was 16 years old, he thought about outracing a light beam. And he thought that if you could race neck and neck with a light beam, the light would be stationary, because you're racing along the light beam. But a stationary wave has never been seen before. And so he said to himself, well, that's impossible. Therefore, you cannot outrace a light beam. But how do you show that? That's just a children's logic. He went to the university in Zurich, the Technion, the ETH, and at the Polytechnic, he learned something called Maxwell's equations. Maxwell's equations were written down about the time of the American Civil War, and they govern light. That's right. The physics of light is governed by Maxwell's equations. It is mathematical. It requires second-year calculus. You have to know a little bit about tensor calculus and partial derivatives. But, yeah, using second-year calculus, you can write down something that describes light. So Einstein took Maxwell's equations and asked the question, can you outrace a light beam? Well, the answer is in the equations. Maxwell himself, of course, died before he could come up with these ideas, but Einstein used Maxwell's equations to show that light has an absolute velocity. You cannot go faster than the speed of light. In fact, the speed of light is a constant, no matter where you shine a light bulb. Now, that violates common sense. If you shine a light bulb to the left, to the right, forward, backward, you assume that light travels at a different velocity in different directions. Nope. Light always travels at the speed of light. Therefore, there must be vast distortions of space and time to make it possible so that the speed of light is a constant. And matter and energy has to also change as a consequence. As you get toward the speed of light, matter increases. Now, this means that the energy of motion turns into matter. E, the energy of motion, turns into M, which is matter. What's the relationship? Well, it's only a few sentences of mathematics. It is E equals mc squared. So E equals mc squared is a rather simple consequence of the fact that nothing can go faster than the speed of light, that light always travels at the speed of light. Okay, well, let's move right on to the next listener phone call.
The name is William, calling from Bountiful, Utah, and would like to know how the atomic energy plants get started up after they get charged with nuclear energy so that they can operate. What actually starts them up and keeps them going? That's my question. Thank you.
Okay, well, there's a simple answer. The core of a nuclear power plant consists of rods, two kinds of rods. One are the fuel rods containing the uranium. That's what heats up the core and creates boiling water, which creates electricity. But there's a second set of rods which absorb the neutrons, therefore quenching the chain reaction, stopping the reactor. The second set of rods is made out of cadmium, zirconium, and boron. These rods absorb neutrons, so they stop the reaction. So how do you stop a nuclear power plant? How do you start a nuclear power plant? To start it, you insert the fuel rod. Fuel rods are there. You remove the control rods. By removing the second set of rods, the neutron count rapidly rises, and you've now turned on the nuclear power plant. To shut it off, you reinsert the control rods, thereby absorbing neutrons, and the chain reaction stops. Now, the name for inserting the control rods to stopping the chain reaction is called scramming. Now, when you hear about scramming the reactor, that means you turn off the reactor. Where did that word come from? It comes from World War II in Chicago when Enrico Fermi was creating the first nuclear reactor. He had graduate students. Graduate students sit on top of the fuel rods with buckets of borated water. If it looked as if the reactor was about to explode or get out of control, he would tell the grad students, scram. At that point, the grad students would dump the boron and get the hell out. Well, that word stuck. So when you want to turn on a nuclear power plant, you turn off a nuclear power plant, When you want to turn it off, you scram it. And that plunges control rods into the core, quenching the chain reaction. To start it up, you do the opposite. You unscram it, you remove the control rods, and the neutron count rises, and the chain reaction starts up all over again. So that's where we start and stop a nuclear chain reaction. Okay, well, moving right along, let's take the next listener phone call.
Dave, Seattle. I wanted to ask a question. How do you know that the universe is shaped like a bubble when we're talking about such large distances that what we actually see in the night sky is billions of years old, because the light, is that old, and we don't actually see the universe as it existed billions of years ago. So how do we know what the shape of the universe is?
Well, first of all, we're not really sure what the shape of the universe is, but let me tell you how we know what we have. First of all, it was Edwin Hubble back in around the 1930s or so who turned one of the biggest telescopes on the Earth toward the heavens, and he measured their color. When yellow light moves away from you, it turns reddish because light waves expand when they move away from you. When the light waves move toward you, the light beams are compressed like an accordion, and then they turn bluish. So when he turned the telescope to the heavens, what did he find? He found a red shift, not a blue shift. The redder the shift, the faster it goes. So therefore, he knew that the universe was expanding. So how do we know that the universe is a bubble of some sort? Well, we're not sure because, of course, we're talking about the universe itself. But here's what we do know. We do know that no matter where you point a telescope in the heavens, on average, you get a red shift. Yellow light is slightly reddish. This means that all the stars are moving away from us. Now, at first, you may say to yourself, well, does that mean that the Earth is at the center of the universe? No. It means that the universe is expanding. And the simplest way to visualize that is to assume that the universe is a sphere. Is it really a sphere? We're not sure. But if the universe is a sphere, and you put dots on the surface of the sphere corresponding to the galaxies, and then you blow up the balloon, all the galaxies move away from you. In fact, the closer they are to you, the slower they move. The farther they are away, the faster they move. That's called Hubble's law. When we actually make the measurements, we find, bingo, Hubble's law is correct. Therefore, the simplest way to visualize it is a sphere. However, other people have said that, well, what about negative curvature? Maybe it's really shaped like a trumpet. Or, for that matter, shaped like a saddle on a horse. They would have negative curvature. So, who is right? Well, the answer is we're not sure who is right because, of course, we're talking about the universe itself. But at the present time, it does seem as if the universe is open. That is, it seems to be infinite for all we can measure, but again, we're not sure. So we use models. The model of the bubble is the simplest to use, so we use it. But hey, we're not positive that the universe is a bubble. Okay, let's move right along to the next listener phone call.
Cornell, we're here in Massachusetts. My question, what exactly is hyperspace?
Well, that's a hot topic today. To find out more about it, get a copy of my book, Hyperspace. It was also a bestseller when it first came out. Well, to be very simple, hyperspace simply means a space of higher dimensions, dimensions beyond 3. We know that there are 3 dimensions to space. In order to describe the size of a book or the location of a building, you have to have at least 3 numbers: length, width, and height. But think about it for a moment. Why 3? There's nothing magical about 3 at all. In mathematics, there are other numbers that are much more magical, but 3 is not one of them. So why should the universe 3-dimensional? Why should it be 3-dimensional? Well, we have the ability to visualize perhaps a 4th dimension or a 5th dimension using mathematics. Now, using common sense, you cannot visualize the 4th dimension. Our brain evolved in 3 dimensions, where saber-toothed tigers lunged at us in 3 dimensions, so we're very good at that. We can manipulate objects in 3 dimensions. We're awful at 4 dimensions, and yet your computer, your PC, manipulates 4-dimensional objects all the time. And so it is possible to visualize the 4th dimension. We cannot do it. Now, I work in 11-dimensional hyperspace, the space of vibrating strings. But when I work in 11-dimensional hyperspace, it's all equations. I don't have to visualize it because the equations track it for me. Now, what would it be like to live in hyperspace? Well, let's say on a tabletop you have people that look like a cookie man living on a table which is flat. This is called flatland. You are in 3 dimensions looking down on Flatlander. You have superpowers compared to the Flatlander. You can, for example, stick your finger anywhere in that world and grab things, so things would literally disappear from Flatland. Or you could put things back down on Flatland like a coin. It would simply all of a sudden appear out of magic. Or you could perform surgery on the inside of a Flatlander without cutting the skin. You can reach inside a closed object and pull out the guts if you want and perform surgery. That's the power of a higher dimension looking down on the 2nd dimension. Now, when I was a kid, I used to go to the Japanese tea garden in San Francisco and look at the carp. I used to spend hours looking at the fish, wondering what would it be like to be a fish. Now, think about it. If you're a fish, your eyes point to the side. You can only see in 2 dimensions, forward, backwards, and that's about it. You live in a 2-dimensional world. And then I imagine that a 3-dimensional person, i.e. me, could reach down and grab a 2-dimensional fish. What would the fish see? The fish would first of all see strange beings that could move without fins, beings that breathe without water, magical beings that could perform surgery without cutting their skin. Think about this. And I put the fish back into the pond, what a tale the fish would have to say. At the turn of the century, many people were fascinated by this idea that there could be beings living in hyperspace. And that's where the idea of ghosts comes in, because some people think that maybe ghosts live in the 4th dimension. And theologians used to write about that. Theologians at the turn of the last century would actually write monographs saying that when people die, maybe their souls go to hyperspace. Well, today we don't know whether hyperspace exists or not. The theory that I work on, string theory, exists in 11-dimensional hyperspace, but that doesn't prove it. So we can visualize it mathematically, but proving its existence has not yet been done. However, at the Large Hadron Collider outside Geneva, Switzerland, the machine got the Nobel Prize for several physicists for working on the Higgs boson. But not only that, we hope to find sparticles. Sparticles are super particles. Particles predicted by string theory. They represent a higher octave of vibrating strings, but we've never seen one. But we think that's what makes up dark matter. Dark matter is invisible, fills up most of the universe, much more plentiful than ordinary matter, and sparticles could be dark matter. So in other words, the next vibration of the string could explain dark matter. We are the lowest vibration of the string, things we can touch. But there are other dimensions out there. So, in other words, the question of hyperspace is no longer academic. Most of the universe may live in hyperspace. Okay, well, let's move right along and take the next listener phone call.
My name is Elizabeth, and I'm calling from Boulder City, Nevada. Bees, why they make hexagons to store the honey in? Why the six-sided shape? Is that the most efficient shape?
Well, yes, it could be the most efficient shape. Realize that if I blow soap bubbles, what determines the shape of a soap bubble? Believe it or not, it is a shape with the minimum area. So, when you get all sorts of crazy configurations of soap bubbles, why? It's because it's the configuration of minimum area. And same thing with the hexagon. It's one of the shapes that allow you to maximize the amount of honey produced with the minimum amount of wax. Pretty good for evolution, I think. Fantastic with Professor Michio Kaku. Let's move right along and take the next listener phone call.
My name is Steve, and I'm calling from Denver. How far does the gravitation of the Earth reach into the space? And does it have anything to do with the objects fallen, such as, meteors and comets, and smashing into the Earth?
Well, you ask a very interesting question. Where do meteors and comets come from? They come from outer space, but how does the Earth grab them? The Earth has gravity, as you pointed out, and the gravitational tug of the Earth will grab onto meteors and comets, and maybe one of these days, God forbid, it will actually hit the Earth. The question is, how far does gravity extend? And the answer actually is infinite. The gravity of the Earth penetrates deep space. Now, you may say to yourself, well, I saw a movie where that wasn't true. Well, those movies are wrong. The sun holds the solar system together by gravity, and the Earth has gravity also, which holds the moon in orbit. But comets and meteors that get too close to the Earth could be pulled in, striking the Earth as a consequence. So we think, therefore, that the dinosaurs themselves were wiped out as a consequence of such a collision 24 billion to 36 billion years ago. We're not exactly sure precisely what happened, but it just goes to show you that A, the reach of gravity is infinite. Oh, by the way, some people say, how can that be when there's weightlessness? Doesn't gravity stop in outer space? How come our astronauts can wave at us upside down unless there's no gravity in space? Well, that's wrong. Outer space has plenty of gravity. But even though it has plenty of gravity, weight can go to zero. Now, how's that possible? Because the moon, for example, is in free fall. It doesn't hit the Earth because the Earth is circular, but the moon is actually in free fall going around the planet Earth. Now, therefore, rocket ships are also in free fall, and according to Galileo, everything falls at the same rate. Therefore, in a rocket ship, you are falling at the same rate that the hull of the rocket ship is falling, and that gives you the illusion that you are weightless. You actually have plenty of weight, except that it's all blurred together because your body tells you, though, that no, it has to be weightless. He's floating. No, you can float even in the presence of gravity. So gravity, in some sense, plays tricks on you. It's invisible, but the more the mass you have, the more gravity you have. And even though the Earth has plenty of gravity, you can still be weightless if you fall at the same rate. Now, I do this experiment for my students in astronomy. I get a small marble, and I get a very large ball, and I drop it. But before I drop it, I ask the students which will land first, the big ball or the little ball. Well, almost everyone says the big ball will fall first because it's bigger and races to the ground bigger. Wrong. You can do the experiment in your own living room. It turns out they both hit the ground at the same time. Now, if one hand is your space capsule, the other hand is your spaceship, you notice that both your hands fall at the same rate. Therefore, that's why gravity can play tricks on you. Okay, well, let's move right along to the next listener phone call.
This is William calling from Alabama, and I had a question on consciousness. What is it, and what are the thoughts behind it?
Well, you ask a $64,000 question of which there's no consensus in the scientific community. So I decided to quantify consciousness myself in my book, The Future of the Mind. I claim that animals are conscious. In fact, I say that the unit of consciousness, 1 unit, the smallest unit of consciousness is a feedback loop like in the thermostat. That's right. I say that even a thermostat has a certain form of consciousness. 1 unit. Now take a look at a plant. A plant may have 10 units of consciousness because it has to know where the sun is located. It has to know where gravity is pointed. It has to know about moisture. It has to know about all these things, which requires a little bit amount of intelligence. Therefore, I would say that animals are also conscious because they also have feedback loops. They have 3 kinds of feedback loops. One is the back of the brain. That's the brain of the crocodile, reptilian brain, the brain of passion, territoriality, fighting. That's the back of the brain. The center of the brain is your limbic system, emotions. Emotions are in the center part of your brain. That's the monkey brain because monkeys are very sociable and smarter than rabbits. So the brain grows from the back to the front. Then the question is, what is in the front, and what do we humans look like compared to the animals? Well, we have the prefrontal cortex, and most animals don't have much of a prefrontal cortex. We know what time it is. We know how wet it is. We know what's going to happen in the future, a decade from now. Animals haven't the foggiest clue about the future. So in other words, I claim that it is our understanding not of position, because alligators can do that, not of our social rank, because monkeys can do that, but projecting into the future. Our brain is a simulation machine. It's constantly predicting the future. Well, unfortunately, our time is up.
Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And this hour, we're going to throw the lines open because this hour is your hour. It's your hour. Okay, well, let's move right along to the first listener phone call.
Hi, this is Steve. I'm calling from Tucson, Arizona. I know that hair on our body is essentially a dead organism. When you cut a hair, there's no nerve, yet hair seems to know how long to grow. The hair on my arms does not grow as long as the hair on my head. If I shave the hair on my arm or leg, it only grows back a certain length. How does the hair know how long to grow? Thank you.
Well, this is a question that could spawn a multi-billion-dollar industry because we're now beginning to understand the genetics and the biochemistry behind the balding process. And think about that. I mean, once we solve balding, there's going to be a tremendous industry set up. Well, first of all, you're right about hair. If you take a piece of hair and put it under a microscope, you don't see cells with nuclei. It doesn't grow like ordinary cells. It's basically pure protein. Yes, that's what your hair is made out of, pure protein. It's not digestible, of course, but it is pure protein. And what governs the growth of a hair? The follicle at the base. And so when some people are going bald, they ask the question, well, when hair falls out, does it grow back? Well, yes and no. First of all, hair grows back pretty much all the time, especially when we're young. And when hair falls out, in fact, we have quite a bit of hair that falls out, 50 or so strands over a period of a few days will fall out of the hair naturally. The new hair keeps on growing to compensate from that. So new hair constantly grows even as old hair falls out. So when hair reaches a certain distance, then the follicle says to itself, okay, time to fall out, and the hair falls out. Now, why is this going to generate a multi-billion-dollar industry? Because we're now finding the stem cells in the follicles which govern the growth of hair. Once we find stem cells, well, stem cells are the mother of all cells. For example, when you have a salamander and you grab it by the arm or leg, sometimes the salamander simply wrenches itself and you're left holding an arm or a leg, but the salamander scampers off into the pond. And later, the salamander's arm or leg grows back. Well, scientists have figured it out. It's the stem cells. It's the stem cells that are still left in the stump that regrows an entire organ. Now, reptiles can do this, amphibians can do this, but we mammals have lost that capability. However, is it possible to revive it? Yes. And that's what some scientists are working on right now, the ability of stem cells to regenerate whole organs. And think about that. Stem cells have been found in the follicle of ordinary hair, which means that even if the hair falls out, one day we might be able to stimulate the stem cells so they regenerate an entire head of hair. And that, of course, could change the whole cosmetics department of your supermarket. And so this is something that scientists are very much interested in. Also on the internet, there is a rather stunning video that you can download. It's a video of a mouse heart. A mouse heart, first of all, that's been separated from the mouse, and stem cells are put inside a cavity, an empty cavity, and over time, stem cells grow into the cavity, creating the tissue of a heart, and then all of a sudden, the heart starts to beat right on the video. It is breathtaking. You realize that you almost feel like playing God, watching stem cells, which are then placed in a scaffolding, grow into the scaffolding, grow into a mouse heart, and then start beating. And so, yes, one day we'll be able to harness this technology. Now, you've probably seen on television and radio ads for stem cell this, stem cell this. I have to say, most of those claims are bogus. I mean, they're just fake. If you follow the research in stem cells, you realize that it's slow, tedious. There are no breakthroughs. We're not going to be able to grow arms or legs anytime soon with stem cells. The promise is there. But, hey, the devil is in the details, and the details have not been worked out. So if you see an advertisement for stem cells to do this and regenerate that, I would hold back. And I would say, well, let me check that out on the internet. And chances are you'll find out that a lot of these claims are actually bogus. So, a word to the wise. The promise is definitely there, but the reality is not quite there yet. Okay, let's move right along to the next listener phone call.
Hello, my name is Roger. I'm calling from Bradenton, Florida, 1280 AM. I was just wondering, when you see some sort of explosion, fireworks and different things, the particles go out in every direction, kind of equally. So in any explosion, you can see the center of it. And I've just been reading lately on the so-called, this Big Bang, that there really is no, it was an explosion, I suppose, of some sort, but I've read that there really isn't a center of the universe where that happened. And I'm just wondering how you would explain that.
Well, that's a key question. In fact, the question is so vital that a monk was burned alive in the streets of Rome in the year 1600 because he said the universe had no center. The man's name was Giordano Bruno. The year was 1600. He claimed that all the stars in the heavens, well, they have planets going around them, and that the universe was infinite, uniform, and therefore had no center. Well, the Catholic Church was not happy at all, Because if every planet has stars going around it, do they have a Jesus Christ? Do they have the sacraments? Do they have sin? Do they have the Trinity? Do they have the Pope? Do they have the saints? I mean, he goes on and on and on. 1 billion Jesus Christ, 1 trillion popes. The mind just goes crazy thinking about this. And then the universe had no center, he said. And that meant that the church was not the center of the universe, and neither was the earth. Well, this was too much for the church. And so what did they do? Instead of confronting the ideas, they simply burned him alive. And 30 years later, Galileo was being put into the same situation, and he was told, do you realize that about 30 years ago we burned your predecessor alive in the streets of Rome? Well, Galileo was no fool, and he quickly recanted all the incredible discoveries that he made with his telescope. So, now let me give you the modern-day approach to this whole question. We think that the universe is a bubble of some sort. The bubble exploded 13.8 billion years ago, and the bubble's been expanding ever since, and we live on the skin of the bubble. So if you live on the skin of a bubble, you ask yourself a simple question. Where is the center of the bubble? Well, if you're on the skin of the bubble, and you can only move around the skin of the bubble, then you cannot reach the center. The center, in some sense, is in the third dimension. And so if you want to know where the center of the expansion of the universe was, in some sense, it's hyperspace. But in our universe, in our bubble, in our skin of the bubble, you cannot point to any one particular point on the skin of the bubble and say, aha, that's the center of the universe. In other words, the universe was very small back then. Space itself was being created. And that's why the universe had no center, because the universe was very small back then. In fact, the universe was so small in principle, you could put it in your pocket. So with the universe being so small, everything was pretty much at the center. And so where's the center of the universe? It's in hyperspace, another dimension. It's not on the surface of our universe. Our universe looks uniform. But if we had a center of the universe would be denser toward the center, just like when you see fireworks, right? The densest part of the explosion is near the center. We see a uniform universe. Everywhere we look, we see that the universe seems to be uniform with no center at all. Now, the idea of hyperspace sounds bizarre to a lot of people, but think about it for a moment. Our universe is three-dimensional. I mean, everybody knows that. Length, width, height determines every object in the universe. When you say time as well, then every event in the universe can be described by 4 numbers. I live in New York. If you want to have someone for lunch, you say, meet me on 5th Avenue and 42nd Street on the 10th floor at noontime. 4 numbers allows you to specify one event, one unique event in the entire universe. But the question is, why? Why should it be 3 dimensions of space? String theory, which is what I work on professionally, says the universe is 10, maybe 11-dimensional. And there were other dimensions that were created at the instant of the Big Bang. We don't see these dimensions anymore because the universe has curled up these other dimensions, but our universe was actually coexisting with other universes. Now, the new wrinkle coming from string theory is that, yes, our universe is a bubble of some sort, but there are other bubbles out there. And so the multiverse of universes obviously had no center. Each bubble has no center, and the multiverse also has no center. Now, string theory, I should caution, has not been experimentally verified. It's just a theory. However, it is the dominant theory in theoretical physics now. You can go to any university on the planet Earth, talk to the leading cosmologists, and they'll say, yes, 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 string theory is one of the leading, if not the leading candidate for a theory of the origin of the universe. And so to answer your question really simply, the universe has no center. The center, if you really want to point to it, would be in hyperspace, but that's another dimension, a dimension that we three-dimensional beings cannot visualize. Sorry about that. Okay, well, let's move right along to the next listener phone call.
Hello, Professor. My name is Rick. I'm calling from Alabama, station 106.5. and I was wondering what your thoughts were on time travel, and do you think it would be possible, in your own opinion, to go back in time and see relevant events? And if that is possible, could we possibly go into the future where the events have not yet been decided or seen? Thank you.
Okay, first of all, yes, we physicists have looked at time travel very carefully. First of all, time travel to the future is not so hard. We do it all the time. And our astronauts even do it even better. They go a fraction of a second into the future by rocketing into outer space, and time slows down inside their space capsule. But to really go backwards in time, going back to the dinosaur era or something like that, that may actually also be possible using Einstein's equations. Now, Einstein had two theories. The first theory, special theory of relativity, would say no. You cannot go backwards in time. You cannot go faster than the speed of light, period. But Einstein was not satisfied with that theory because gravity was missing. And when Einstein came out 10 years later with the theory of gravity, he said that space and time is like a trampoline net. But a trampoline net can do more than warp. It can also rip. And that's what Einstein thought about very deeply. His equations allow for time travel. That doesn't mean that time travel exists. It just means they are valid solutions of Einstein's equations. For example, Einstein's next-door neighbor at Princeton was one of the greatest mathematicians of the century, Kurt Gödel. And Kurt Gödel, being the mathematician he was, found a solution of Einstein's equation which allowed for time travel. If the universe rotated, and you went around the center of the universe, then you could come back yesterday. You could go backwards in time. Now, Einstein was very disturbed by this. In his memoirs, Einstein said, yes, my next-door neighbor has just found a solution of my own equations which allow for time travel. But then he said, on physical grounds, I can dismiss it. In other words, the universe expands, it doesn't rotate. Now, the universe expands because of the Big Bang Theory. However, if the universe rotated, then it means that time travel could become commonplace. Well, in the decades since then, we've discovered black hole solutions. Some of these black hole solutions allow for time travel. Then this whole question becomes of paramount importance. If I have a wormhole, a gateway through space and time, a rip through the fabric of space-time itself, on the other end of the wormhole could be the past. This is a valid solution of Einstein's equations. So what's the catch? There's always a catch someplace, right? Well, first of all, to create this hole in space, you need a black hole. And not everyone has a black hole ready. But the other condition I'll get to after the commercial break. So after the commercial break, I will try to answer the question, can you go backwards in time and meet your teenage mother before you're born and have her fall in love with you? What happens then? Okay, let's move right along to the next listener phone call.
Robert, Las Cruces, New Mexico. Why is the definition of life tied so closely to DNA? I suspect that somewhere in the universe there may be life that doesn't equate to DNA.
Well, I agree with you. I think that life does exist throughout the universe. So far, we have found 3,600, count them, 3,600 planets going around other stars, of which about 20 of them look very much like the Earth, except they're a little bit heavier. So I think the galaxy itself could be teeming with life. In fact, we think that the Milky Way galaxy has billions, I repeat that, billions with a B, billions of Earth-like planets. So the next time you go outside tonight, look up in the heavens, realize that somebody could be looking back at you. And then the question is, well, if they come to Earth and land on the Earth, what do they want? Do they want to eat us? Do they want to mate with us? Favorite themes from science fiction? No, because perhaps they're not going to be made out of the same DNA. DNA is a molecule. That's all it is. But it has two characteristics. One, it stores information. There's a code along the DNA molecule. And second, it reproduces itself. Now, here's a question for you. How many molecules can reproduce themselves? Can water do it? H2O? No. Carbon dioxide? CO2? No. None of those molecules can make copies of themselves. And that's what DNA does. Then the third question is, what else can do that? And the answer is, we don't know. However, we suspect there must be other DNA-like molecules that are out there. For example, just about, I think 2 years ago, there was a group that claimed that a form of DNA with arsenic was found inside. One of the molecules of DNA was replaced by the arsenic atom. That result still has not been proven conclusively, but it just goes to show you that if you take our own DNA molecule and replace some of the atoms with other atoms, you might be able to create a carbon copy of DNA that is chemically different, that has different chemical properties, but reproduces itself. So here's a question. Are there other forms of DNA out there? Well, even on the planet Earth, people have asked a simple question. On the Earth, why don't we have 2, 3, 4 types of DNA? We think life got off the ground on the Earth about 3.5 billion years ago. We're not sure, but we think that roughly 3.5 billion years ago, one molecule was created, DNA. And we are descendants of that one molecule because it reproduces itself. Just like the Sorcerer's Apprentice, when Mickey Mouse reproduced broomsticks, we think that reproduced all the DNA. But the question is, why aren't there 2, 3, 4 different types of DNA? The answer is, we don't know. Are there other forms of DNA that we haven't even thought about, that we haven't even created? And the answer is certainly yes. In fact, when I see Star Trek or I see Star Wars, I see the aliens, I say to myself, come on, give me a break. They look just like us. Why should life in outer space look just like us? And for that matter, why should they have the same DNA as us? Of course, they're going to have different kinds of chemicals, but DNA is rather versatile. First of all, it's based on carbon. Carbon has 4 bonds, meaning that it's very easy to create proteins and chains of carbon atoms. So yes, carbon is quite useful because it creates all sorts of organic chemicals. So we do expect that intelligent life in the universe may be based on carbon, but there's got to be other molecules other than DNA that can contain information and reproduce itself. Okay, well, let's move right along to the next listener phone call.
Hi, my name is Rachel, and I was just calling because when I was in school, I had a teacher that told us that everything has its own gravity. Go over all this on the radio with mass and gravity and their relationships, and just give a general overview of the whole idea. Thank you. Bye.
Okay, well, you're absolutely right. Your science teacher was correct. Everything has gravity, and everything attracts each other. Now, you may say to yourself, well, that can't be right for 2 reasons. First of all, I don't feel gravity attracting things to me. There's a table in front of me with a book on it. I'm not attracted to that book, and the book is not attracted to me. Second of all, what about weightlessness? I thought in outer space things are weightless, so there's no gravity in outer space. So it can't be right. Objects cannot have gravity, because why aren't books and tables attracted to me? And in outer space, how come there's no gravity? Well, let me answer those too. First of all, Isaac Newton and your science teacher was right. Everything has gravity, but the smaller it is, the weaker the gravity is. So yes, it's true that that book in front of me is attracted to me. I am attracted to that book. We both have gravity, but it's so tiny, it's so infinitesimal that you can barely measure it. For example, the Earth weighs, 6 sextillion kilograms? That's the weight of the planet Earth. But it takes a mass of the Earth that big to hold me on to my chair. So why am I sitting in my chair? I'm sitting in my chair because there's an object next to me that weighs 6 sextillion kilograms called the planet Earth. It takes that much dirt, a huge amount of dirt that's, 8,000 miles in diameter? It takes that amount of dirt to create gravity that can attract me to my chair. That's how weak gravity is, but across the universe, it's the only game in town. It's what holds the solar system together. Now, the next question is, well, if there's gravity everywhere, then how come weightlessness exists for our astronauts? Well, weightlessness simply means you have no weight, but there's plenty of gravity out there in outer space. Our space capsules are hurled around the solar system precisely because of the sun's gravity. So why are things weightless? Because everything falls at the same rate given a certain distance. So in outer space, your rocket ship falls toward the Earth. But you inside the rocket ship fall at the same rate. Therefore, you have the optical illusion that you are weightless because you are falling. There is gravity, but you're falling at the same rate as a rocket ship. So here's an experiment. I don't advise you to do it, but here's an experiment. Go inside an elevator and then cut the cable. Please do not do this experiment. You cut the cable, you'll find out you are weightless. But there's plenty of gravity when you hit the floor. Does everything have gravity? The answer is yes. And then the other question is, well, if there's gravity everywhere, then how come our astronauts have no gravity? Well, actually, our astronauts do have gravity. They have no weight because weight and gravity are different. So here's an experiment. Go to a theme park, and in many theme parks, they allow you to climb up a long tower, and then they drop you inside a capsule. Inside the capsule, you are weightless, but you have gravity. Why are you weightless? Because the capsule and you fall at the same rate, giving you the optical illusion that you are weightless. Now, here's an experiment that I do for my astronomy class. I get a large object, like a shot put, and a small object, like a pea. And then I ask the audience, which will hit the ground first if I drop them at the same time, the pea or the shot put? Well, the class says, this is an easy one. The shot put obviously hits the ground first. Well, then I do the experiment, and lo and behold, they both hit the ground at the same time. Now let's say I have you in one hand and a capsule on the other hand. Which will hit the ground first? Well, most people would say the capsule is so heavy, the capsule will hit the ground first. No, if I drop you and the capsule at the same time, you both hit the ground at the same time. Then if I put you in the capsule and drop you, you float. You float inside the capsule because you are falling at the same rate. So, in other words, because objects fall at the same rate, you have the optical illusion that you are weightless. So in outer space, there's plenty of gravity in outer space, but there's no weight because you're falling at the same rate that the rocket ship falls. Okay, let's move right along now to the next listener phone call.
Hi, my name is Trevor. I am from Round Valley, Arizona, and I would like to know why, if you are, say, standing inside a semi-truck, if you jump, you don't go to the back while it's going at 60 miles an hour. Thanks for your time, and goodbye.
Okay, well, that's a question that a lot of people ask because many of us have been in cars and wonder, gee, inside the car, because you're traveling at 60 miles per hour, inside the car, everything seems normal. If you drop a sheet of paper inside a car, it falls just as if you're stationary. And why is that? Well, you've seen these old World War II movies. In these old World War II movies, the cameraman sits right there at the bomb bay, dropping the bombs. They open the bomb bay, and the bomb drops. And does the bomb fall away to the back of the airplane? No. The bomb drops directly behind the camera as if the airplane were at rest. So that's the answer to your question. You are in what is called an inertial frame. Inertial frame is a frame traveling at constant velocity. And so the first law of Isaac Newton says that objects in motion stay in motion forever as if they were at rest. So inside your car, you're traveling at 60 miles per hour. Inside the car, everything is normal. You are in an inertial frame. And the first law of Isaac Newton says that inside your car, the laws of physics are the same as if you are at rest. So if you drop a bomb out of the bomb bay of an airplane going at hundreds of miles an hour, the bomb drops straight down. You can see the bomb drop as if your airplane were at rest. This is also true in outer space. Our astronauts travel at 18,000 miles per hour. It's a huge velocity in outer space. But do they see objects falling to the back of their space capsule if they jump? No. It's as if the space capsule were at rest. And that's an example of Newton's laws of motion. That objects traveling at a constant velocity, the laws of physics are the same as if they were stationary. And that's why in a speeding car, everything feels as if everything is totally at rest inside a speeding rocket or inside a speeding car. It all goes back to Newton's first law. Okay, well, let's move right along now to take the next listener phone call.
My name is Wesley. I'm calling from Chattanooga, Tennessee. My question is about when a satellite is orbiting the Earth, on the TV it shows a big zigzag, and I wonder if that's due, in fact, to the speed of the Earth and the speed of the satellite, or why that's so. But anyhow, that's my question.
Well, I'm not quite sure what you mean, but when a rocket fires, it moves in a straight line because of the curvature of the Earth and the spin of the Earth and so on and so forth. It then curves, arcs across as if it goes in a huge circle. However, as the satellite goes around the Earth many times, and you were to graph the trajectory of the rocket as it moves along the Earth, you have many parallel lines. So even if a rocket is launched from Florida and it starts to orbit the Earth, you do not have the orbit going over Florida constantly. No, it starts to go over maybe Texas. It starts to go over maybe the Atlantic Ocean because the Earth is spinning beneath the satellite. And so when satellites go around the Earth and you put the trajectory on a gigantic screen, it does not go around Florida forever. No, it starts not to go into a zigzag, but it seems to go in a spiral because the Earth spins underneath the rocket. In fact, in 90 minutes, the satellite will go completely around the Earth as the Earth spins. Okay, well, unfortunately, we've run out of time. Once again, this is Science Fantastic with Professor Michio Kaku. Join us every week on Science Fantastic as we probe the mysteries of nature.